Okay, welcome. So today we're going to talk about finding volume. So we're moving away from 2 dimensions with the area and going to move into 3 dimensions with volume. So the sort of way we're going to start out with are dealing with weird solids is sort of what I call them, because they're weird. They're weird to picture. They're weird to like imagine what they look like. They're weird in the sense that like they're made up of like sort of like Frankenstein pieces, but they're physically possible, and thus we're going to find some volumes here. So the first one is right here. We got the base of a solid is circular with a radius of 1, and then parallel cross sections perpendicular to the base are equilateral triangles. Okay. So some words in here that might be sort of weird. So let's start with this. I think about all of these problems as if I'm dealing with loaves of bread. So the loaf of bread here in this case has a bottom that looks like a circle. So that is sort of like the bottom of loaf. So if I took my loaf of bread and I just like flipped it over and looked at the very bottom of it, it would be more brown than the rest of the bread, a little bit crispier because it was closer to the heating surface. But it was also looked like a circle is what was happening here. And then I think about the cross sections as being sort of like the slices of bread, okay? And it makes sense here. So it says here like you're doing parallel cross sections. Well, like when you cut bread out, you don't cut them at different sort of angles from each other. Well, I mean, you could do that, but like your whole family would probably be like, what is wrong with you? So instead you cut slices of bread like, you know, here's my knife, I go shh, and then I cut the next one. I mean, now we have pre-sliced bread, so that's maybe not a thing you're so familiar with, but it's the same thing when the pre-sliced bread comes out. They're all parallel to each other, not all weird. And then they're perpendicular to the base. So the cuts are going straight down into the base, not at like an angle this way. So it's hard to tell with the video here, but you cut straight down into the cutting board. You don't cut at a weird angle. So that's all this is saying here. So the question I often get with these is like, well, what does this look like? Like, what does this solid look like? A circle base and equilateral triangles as the slices? Like, what does that look like? The answer is it's not important necessarily. If you really wanted to know, like we could do maybe a quick sketch and then you'll see how like unhelpful it is. So like start with the base and the circle. Well, if you're looking at it sort of as an angle, it would sort of look like an oval. So, you know, if I was up above, I'm staring down, it look like a circle, but from the side it looks like this. And then equilateral triangles are sort of like this, right? So something like that. So like there's sort of like a spine to this. I didn't quite draw that one as well. So yeah, like that's not very helpful. You want to know like what it actually looks like? If I had a 3D rendering, in the textbook here, it shows, it looks like this. To me, it's like the back of like a brontosaurus, basically. That's what it looks like to me. But not helpful. Not very helpful at all to sketch it. So that's why I always say, like, don't worry about it. Just focus on the 2 pieces of info they gave you. First off, it's a circle. That's the base of it. Okay. So let's draw the circle on the coordinate plane. So sometimes they tell you put that base on the coordinate plane, and sometimes they don't tell you that, and you have to figure that out for yourself. So let me do that because I have to figure it out for myself. So here's a circle. I'm centering at the origin because that seems like the simplest sort of choice. But you could put this circle anywhere. In fact, like if you want to after this video, put the circle someplace else. Put it center at like 2, 2. And notice how you get the same volume at the end of all of this, okay? So yeah, it goes at 1, 1. So what's the equation of this circle? We'll door explore this. That's right. It is x squared plus y squared equals 1. Good job. Pause for answers. Yeah, if you don't remember this about circles, pop in. We'll talk about why this is the equation of a circle, because that's an expectation, is that if I tell you there's a circle with a radius of blah, that you go, great, like I know what that equation is, no problem. Okay, next thing, let's talk about the cross section. So this is sort of like staring down at the bottom of it, or from the top, you can think about you being like up above this loaf of bread. So what we're going to do is we're going to take our knife and we're going to make a cut here and here. That's just where I'm cutting it. You could do it over here, more towards the center, whatever. So cut, 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 cut. All right, so if I take this loaf of bread, I make my 2 bread cuts here, and I pull it off over here, the piece of bread that I'm pulling out will look like an equilateral triangle. I'll mark it that way so that way we're aware. Equilateral. Great. And it's got a little bit of thickness to it. So I'll draw that in here. It's got a tiny amount of thickness. And so that's sort of like the piece we're seeing. So the other side of this would also be shaded, because like this right here is maybe this shaded part. And then the other side over here is this shaded part. So like you saw in the picture, this is coming up out of the paper and bumping up a little bit. Okay, and so here's the real goal to start out with. What is the volume of this, just this slice of bread? All right, well, we can start with the simplest thing, which is thinking about, well, how thick is it? Coming back over here, the thickness is this tiny horizontal length. It's a tiny change to the x values. We are well versed and hopefully now knowing that's dx. Okay. Well, how do I find the area of a triangle? Area is equal to half the base times the height. Cool. So I'm interested in what is this height here. I'm going to label it h. I'm interested in what is this base here. I'll label it b. So b, this length here is actually the length from the top to the bottom of the circle. How do I find that? Well, I'm interested in what is this y value and this y value. Symmetry tells me they're going to be opposites of each other because it's a circle. So how do I find them? Well, let's take our equation and let's solve for y. Let's see what we get here. So if I subtract over the x squared, I get this. And if I take the square root of both sides, I get this. And there are actually 2 outputs, which makes sense. I'm expecting to find 2 outputs for the same slice of bread here. So there's going to be the positive side of the circle, that's above the x-axis, and the negative side, that's down below here. Great. So then what's the base length going to be? Well, the base length, and this is going back to thinking about area, well, that's going to be this top y value subtracted by the bottom y value here. So b equals, the top one is the positive square root, subtracted by the bottom square root, which is the negative part of it. And since we're subtracting a negative, we can add, so that gives us 2 square roots 1 minus x squared. Awesome. Okay, next step, finding the height. Okay, this is an equilateral triangle. I haven't used that fun fact yet, so I'm betting that I can get to it through there. Let me think about this. I know there's like some rule about like how all the side lengths compare to each other in an equilateral triangle. I don't remember it though. So let's do some creating of links and notice some stuff here. So here's what I notice is that if I chop my equilateral triangle down along the heights there, I get a right triangle. Right triangles have so many things going on with them. So I'm going to do that. So I'm going to sidebar over here. This is my sidebar for finding the height of that triangle. Okay, so cut it in half. What do I get? I get this. The hypotenuse, since it's an equilateral triangle, is b, which is that length there. This leg down here is half of b. And then this is the height. That's what I'm in search of. Okay, so I'm going to go with Pythagorean theorem. FYI, you could go sines and cosines and tangents and stuff like that. And if you remember your trig ratios, you can figure this out too. But Pythagorean theorem is like the first thing that popped out to me because I had all the side lengths. So what is my Pythagorean theorem? It's going to be half of b quantity squared plus h squared equals b squared. So that's 1/4 b squared plus h squared equals b squared. If I subtract that over, h squared equals, well, this is 1b squared. I'll subtract a third, or fourth, so that's 3/4 b squared. And then now I'll take the square root of both sides. So that gets me the square root of 3/4 b squared. So let's chunk this up here. H is the square root of 3. That's just the square root of 3. Sad face. Square root of 4. Oh, that's 2. Square root of b squared. That's b. Technically the absolute value of b, but since we're dealing with all positive lengths here, that will be just b. Awesome. So now I have a relationship on how to compare h to b. So now when I come over here, and I'm thinking about, well, what's h? H is going to be equivalent to the square root of 3 over 2 times b, which is the square root of 3 over 2 times, and b is 2, times the square root of 1 minus x squared. Times 2, divide by 2. That leaves us with just the square root of 3 times the square root of 1 minus x cubed. And since those are both square roots, you can take the 3 and bring it underneath. I'm not going to do that because of something you'll notice in just a moment. I'll try to point it out to you. So now let's go into setting this all up. So where are we? If you remember, our miniature goal was just to represent the volume of this slice of bread as generally as possible. So let's do that. So the first thing you do when you're finding the volume of a prism, what's the area of the face that you're looking at there, or the face here in this case? Sometimes you call it the base. So volume equals, we'll leave some space. So 1/2 the base of the triangle, which we found to be this. So 2 times the square root of 1 minus x squared, times the height of the triangle, which we found to be this. Square root of 3 times the square root of 1 minus x squared. So that's the faces area here. So that's this area. And then now we want to multiply it by how thick it is, which is dx. All right. Well, the goal here wasn't to find the volume of just that slice of bread. The goal here is to find the volume of the entire solid, the entire Brontosaurus back. Well, I just pulled out one slice of bread. In theory, there are infinite of them. So if we want to create an infinite number of them, we're going to go the integral. And then we got to think about, well, where do we start with our slices of bread? Well, we start way over here on the left. Right here at -1 is the very first slice of bread, and then we build them and stack them side by side by side by side by side until we get to the last one, which is there at +1. So our integral will be from -1 to 1. All right, if you're looking at this and you're like, that looks scary, let's do some beautification before we try to dive into it here. So let's see, what do we first notice? The first thing I notice is I got half of 2, so bye-bye, those undo each other. What I also notice is that I have the square root of blob times the square root of blob. So if I think like, oh, the square root of something times the square. Like that's just the square root of blob quantity squared. And those undo each other, leaving me with just 1 minus x squared. So those two things multiply to that. Try it out with numbers if you're not sure. You're like, wait, I don't get it. Like, try it. Like, square root of 3 times the square root of 3. Simplify that and see what happens. We still have this square root of 3, so we'll bring that out. And then we still have the dx. That goes back there. And then, since this is a constant multiple, I can bring that out in front and not have to worry about it until the very end. And so now I just have this really nice integral that I can, forgot the negative one there. Really nice integral that I can do by hand, or I can do it with a calculator at this point. Notice that at no point did we really need a calculator. Circles are simple shapes, and all of this should be able to be done without a calculator. So I'm going to finish it up without a calculator, because some of you still had questions about, like, wait a minute, I forgot, how do I evaluate a definite integral again? So let's do that. So it'll be the square root of 3 times, let's go antiderivative mode, x minus a third x cubed from -1 to 1. All right, so let's evaluate at 1. So that's going to be 1 minus a third subtracted by, and this will be -1 and then plus a third, because -1 cubed will be negative, negative times a negative, positive 1/3. Okay, and then now we simplify. So 1 subtracted by -1, that will be 2. Negative a third minus a third, that's negative 2/3. Okay, so square root of 3, this will be, that's 6/3, right? Yeah, 6/3 minus 2/3 gets us 4/3. So what's our answer? 4 root 3 over 3. That is the volume of this, which is, I don't know, approximately what? You can figure it out later on if you wanted to approximate it. Okay, so let's recap. Step 1, don't draw the solid. That's not important, and it's not going to help you, and oftentimes you're going to be like, I can't picture it. And that's kind of the point of the problems here, is like, these aren't the typical solids you can picture, but you can sort of use the information to help you out. So how do you do that? What's your base look like? Graph it, come up with an equation for it if not given. Think about taking a slice out of it. What's it look like? It tells me it's an equilateral triangle. Draw it with a little bit of depth. Goal 1. How do you find the volume of just this slice? So you got to dig in. How can you represent the different lengths based on this over here? So there's always a connection back, always a connection back. So if you're stuck, notice, go back. What do you notice about this? Sometimes you have to do a sidetrack. So to create some links, I had to do all this work here. I didn't know how to represent the height, so I did some work. Again, this is not the only way to do it, but this is what I had to do. And then start with just, well, how do you find the volume of just that slice? So that's the area of the face of it times its depth. And then think about infinite number of them from where to where and evaluate it all the way out. Something to note is that it is totally possible that you could have called the slices going this way. And because of the symmetry of a circle, you end up with the same volume. And it's not clear which way you should make the cuts. If you're going that way, note that you're going to be doing things with respect to y instead of x, because you're cutting this way is a cut that's a tiny sort of change to the y values. So then everything will be in terms of y, but it actually doesn't change anything. Like you would just end up doing all this same work again, except for everywhere there's an x would be replaced with a y, and you get the same answer. All right, so please take the survey at the end And I will check out your questions. I'll check out to see if you understand how to set this all up. And we will do some practice in class. Thank you.